Hello everyone and welcome to the OneClass channel. My name is Donna and I'm a recent master's graduate from the Material Science program from the University of Ontario Institute of Technology, also known as Ontario Tech University. So today we're going to go over some commonly asked questions in chemistry at the high school, college, and university level. So if you needed any help with homework or with tutoring, then check out the links in the description below. Now let's just get started on our set of questions for today's session. Okay, so question 1 just asks, what are the resonance structures for sulfur dioxide? Okay, so to write out the resonance structures, I'm first going to write or draw the Lewis structure of sulfur dioxide. So when we want to write out the structures, I first want to find out the total valence electrons of the molecule. So in the case of sulfur, it has 6 valence electrons, and in the case of oxygen, it also has 6, but there are 2 atoms of oxygen, so I'll be multiplying this by 2. And then when we add them all up, we end up getting a total of 18 valence electrons. Okay, so now I'm going to draw sulfur as the central atom and the oxygens as the terminal atoms. Okay, so recall that each bond contains 2 hydrogens, two electrons. So far I have drawn 2 bonds, so that is 4 electrons in total, and I need to have 18. So I know one of them will have a double bond. And I'm just going to draw the rest of the lone pairs on all of the oxygens. Okay, so now let's count out how many electrons I've drawn so far. We have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Plus the bonds. So there are 3 bonds, so add 6. So we have 16 drawn so far, but I need 18 in total. So now I'm just going to put another 2 as the lone pair on sulfur. Okay, so now these have charges. Sulfur has a positive charge, and oxygen has a negative charge. Okay, so this formal charge structure is actually preferred since oxygen is more electronegative than the sulfur. It will most likely carry the negative charge. So this is one resonance structure, and we can draw the second one, switching which oxygen has that negative charge. So now I'll show the leftmost oxygen atom with only a single bond and a negative charge. And now the sulfur still keeps its positive charge. And these are 2 examples of the resonance structures for sulfur dioxide. So the junior tutor said that the 2 resonance structures of the given molecule are shown below. There are 18 valence electrons, 6 from sulfur, 6 from oxygen. I think they mean like 12 from oxygen in total. And these 6 electrons form 3 bonds, and the rest are distributed among the atoms to complete their octet. Okay, so this solution is correct. Okay, so question 2. What is the mechanism for esterification? Okay, so let me write out the general scheme. But when we have a esterification reaction, this involves the conversion of a carboxylic acid ester into a different carboxylic acid ester. Okay, so pretty much the R group on the ester changes. Okay, so now I'll draw out the mechanism. And for this mechanism, let's say that it occurs in acidic conditions. Okay, so step 1, we have our ester, which pretty much looks like a carboxylic acid group, except instead of it being at the end, it has another side group attached to the oxygen instead of hydrogen. And it has double bonded oxygen in the middle. So this is an example of an ester. And step 1 is the protonation of the carbonyl. Let me write that up here. Okay, so again, this occurs in acidic conditions. So one of the lone pairs on the oxygen will come in and attack a proton in the solution. So now we're left with our ester and the protonated alcohol group. So this is where our second ester or alcohol group comes in, and it has the desired side group that we want to use to replace the old side group, and it's in the form of an alcohol. So the second step is a nucleophilic attack. So one of the lone pairs on this alcohol comes in and attacks this carbon, and it neutralizes the positively charged oxygen. So now we have an alcohol group up here. We have our side group R1, and now we have a newly formed bond and a new side group R double prime. So this oxygen has a positive charge, but step 3 is just a proton transfer. So I'll show that this proton will be transferred to the other R group. So here is the proton transferred to the second oxygen. And now what happens next is the removal of the leaving group. So one of the lone pairs on this oxygen comes down and kicks off this entire group. Let me just write down the name of this step. Is the removal of the leaving group. So now this oxygen has a double bond and is positively charged. And you can already see that a new ester is formed with the R double prime side group. Draw the hydrogen on this end. Because the next step is the removal of that proton. I'll just say step 5 is deprotonation. And then this leaves us with a new carboxylic acid ester, and H3O plus was formed in the process. And let me just box out the new ester. Okay, so this is the basic mechanism, and this is taking place under acidic conditions. So it would be a little different in basic conditions, but you should end up with pretty much the same, like different carboxylic acid ester. So let's see what the junior tutor said. Transesterification is a chemical reaction used for the conversion of triglycerides contained in oils into usable biodiesel in the presence of a catalyst. Yep, so this is one this is one way people can use transesterification in the real life. The triglyceride reacts with methanol in the presence of an acid or base catalyst. This produces diglycerides and methyl ester. The diglyceride will react further to the alcohol to produce monoglycerides and a methyl ester. Continuing the process, it would have the products glycerol and a methyl ester. Okay. So they pretty much show a reaction scheme of the conversion of triglycerides Okay, so I'm just going to say that this solution is a good example of one of the applications for the transesterification reaction. Okay, so I just said that this solution is a good example of one of the applications for the transesterification reaction. However, the actual mechanism is not shown. Okay, so question number 2, or 3, I guess. Yeah, 3. Question 3. Consider the following formulas for N-pentane and neopentane. So let's draw them out. Okay, so pentane has 5 carbons, all in a line. And now let's look at neopentane, which also contains 5 carbons, but you can see that the molecule is much more condensed. Okay, and this is neopentane. Okay, so the question says that both compounds have the same overall formula. They have molecular formula, C5H12, that's the same. And they also have the same molar mass, which is 72.15 grams per mole. Yet, N-pentane boils at 36.2 degrees Celsius, whereas neopentane boils at 9.5 degrees Celsius. Rationalize the differences in the boiling points between these two nonpolar compounds. So, in the case of pentane, you'll notice that it is a longer molecule. And in the case of the neopentane, it is shorter, shorter chained, I guess. So because the pentane is longer chained, it has a much higher surface area. Well, it takes up more surface area. And because of this, it feels stronger dispersion forces. So therefore, these longer chained molecules are expected to have a higher boiling point. Okay, in the case of the neopentane, since it feels less of the dispersion forces, it has a lower boiling point compared to the pentane. Okay, so let's see what the junior tutor said. Both alkane compounds are nonpolar, and the only intermolecular forces that exist are weak van der Waals dispersion forces. The longer the alkane carbon chain, the higher the boiling point is, since the long chain has a constant contact surface area, which will attract a higher amount of intermolecular van der Waals dispersion forces. The longer carbon chain N-pentane molecule is thus expected to have a higher boiling point than the shorter chained and branched neopentane molecule. Yep, so this solution is correct. Okay, so question number 4. Thiophene is a liquid compound of the elements carbon, hydrogen, and sulfur. Sample of thiophene weighing 7.96 milligrams was burned in oxygen, giving 16.65 milligrams of carbon dioxide. Another sample was subjected to a series of reactions that transformed all the sulfur in the compound to barium sulfate. If 4.31 milligrams of thiophene gave 11.96 milligrams of barium sulfate, what is the empirical formula of thiophene? Also, its molecular weight is 84 atomic mass units. What is its molecular formula? Okay, so this question is actually a good question. It is multi-stepped, but let's go over all the steps one by one. Okay, so the first part of the solution is to find the mass of carbon. So the question says that when a sample of thiophene weighed 7.96 milligrams, it gave 16.65 milligrams of carbon dioxide. So first we need to find the mass percentage of carbon that is in carbon dioxide. So mass percent of carbon. And to do that, we are going to take the molar mass of carbon divided by the molar mass of carbon dioxide. And if we multiply this by 100%, this will give us the mass of carbon in carbon dioxide. So the molar mass of carbon you can find on the periodic table is 12.1 grams per mole, and the molar mass of carbon dioxide is 12.01 plus 2 times the molar mass of oxygen, which is 32. Okay, so multiplying this by 100. The mass percentage of carbon in carbon dioxide is 27.29%. Okay, so now that we know how much carbon is in carbon dioxide, and we also know that the sample of thiophene gave off 16.65 milligrams of carbon dioxide. If I multiply this by however much of it was carbon, so the 27.29%, then we can find the mass of carbon in the sample. So 16.65 milligrams of carbon dioxide multiplied by 0.2729, so this is the percentage in decimal form, gives us 4.54 milligrams of carbon. And to specify, this was in 7.96 milligrams of thiophene. Okay, so we have the mass of carbon. Now for part 2 of the question, we want to find the mass of sulfur now. Okay, so to do this, we're going to do something similar. We want to find the mass percent of sulfur in barium sulfate. So the mass percent of sulfur is equal to the molar mass of sulfur divided by the molar mass of barium sulfate. So the molar mass of sulfur is 32 grams per mole, and the total molar mass of barium sulfate is 233.38 grams per mole. Okay, so now we want to take the fraction, multiply it by 100, and you should get 13.71%. Okay, so the question says if 4.31 milligrams of thiophene gave 11.96 milligrams barium sulfate. So I'll show that 11.96 milligrams of barium sulfate has the 13.71% of sulfur. So I'm going to multiply this by 0.1371. And you should get 1.64 milligrams of sulfur. But this is only in the 4.31 milligram sample of thiophene. And I want to express this in the same mass of thiophene as my carbon. So to find that, we need to do an additional step, just showing the ratio of the masses. We can find the sulfur in 7.96 milligrams of thiophene. So we know that 1.64 milligrams of sulfur is in the 4.31 milligram sample. And we are looking for how much sulfur is in 7.96 milligrams of thiophene. I'm going to say total instead of thiophene. So now we pretty much just have to solve for x. And you get 3.03 milligrams of sulfur. And this is in 7.96 milligrams of thiophene. So let me box this mass as well. Okay, so step 3. We know that thiophene only contains carbon, hydrogen, and sulfur, so now we just need to find the mass of hydrogen in the sample. So the mass hydrogen is equal to the total mass, which is 7.96 milligrams. Subtract the mass of carbon, which was 4.54 milligrams. And then we're going to subtract the mass of the sulfur. And we end up with 0.39 milligrams of hydrogen. Okay, so we have the masses of all three components of thiophene, but the question doesn't end there. We need to then find the number of moles of each of these atoms. So I'm going to do this on the next page. So question 4 continued. And step 4 is to find the number of moles. So let's do carbon first. The mass of carbon was 4.54 milligrams. But when I want to calculate for number of moles, I'm going to convert my milligrams to grams. So to do that, we just divide by 1,000 or multiply by 10 to the negative 3. So this is the value in grams. And the equation for number of moles is mass over molar mass. So the molar mass of carbon is 12.01 grams per mole. So the number of moles in the sample is 3.78 times 10 to the negative 4. And this is for the moles of carbon. Now let's do the same thing for the sulfur. Its mass was 3.03 milligrams, but to convert to grams, I'm going to multiply by 10 to the negative 3. And the molar mass of sulfur is 32. So if we divide mass over molar mass, you get 9.47 times 10 to the negative 5, and this is moles of sulfur. And now for the number of moles of hydrogen, it had 0.39 milligrams. So again, I'm going to convert it to grams and then divide by the molar mass of hydrogen, which is 1.01 grams per mole. So now this gives 3.86 times 10 to the negative 4 moles of hydrogen. So now step 5 is to find the empirical formula. And to do that, I'm going to write down all the atoms and then divide by the lowest number of moles. So this number of moles for sulfur is the lowest out of the 3. So for carbon, it is 3.78 times 10 to the negative 4 divided by 9.47 times 10 to the negative 5. And for hydrogen, it is 3.86 times 10 to the negative 4 divided by 9.47 times 10 to the negative 5. And then for sulfur, it's just dividing its moles by itself. That always gives just 1, but I'll show the work. And then when we do the division step, we want to round to the nearest whole number. So when we do this, we get C4H4S. So now for step 6, we can find the molecular formula. So to do this, we first want to find the total mass of our empirical formula. So it was 4 times the molar mass of carbon plus 4 times the molar mass of hydrogen plus the molar mass of sulfur. So I can try to fit it going across. 4 times 12.01 plus 4 times 1.01 plus 32. And you'll notice that the molar mass of the empirical formula is also equal to 84 atomic mass units. So this tells us that our molecular formula is the same as our empirical formula, which is C4H4S. Okay, so pretty long question, but we made it through. Let's see what the junior tutor said, and I'll go back to the first step. Step 1, calculate the mass of carbon in 7.96 thiophene. So the mass of carbon in thiophene is equal with the mass of carbon in carbon dioxide based on the law of conservation of mass. The percentage of carbon in carbon dioxide is 27.29%. So this percentage of 16.65 milligrams of CO2 is 4.54 milligrams of carbon. Step 2, calculate the mass of sulfur in 7.96 milligrams thiophene. So the mass of sulfur in barium sulfate is equal with the mass of sulfur in 4.31 milligrams thiophene based on the law of conservation of mass. So I think they meant to put sulfur instead of barium for this mass percent. But anyways, they still did the correct math and got 13.71% sulfur. So that means 1.64 milligrams of sulfur is in the 11.96 milligrams of barium sulfate and also in 4.31 milligrams of thiophene. But to find the mass of sulfur in 7.96 milligrams of thiophene, they showed how the ratios compared with the 4.31 milligrams, and they found that 3.03 milligrams of sulfur was in 7.96 thiophene. Now to find the mass of hydrogen, I think it's just missing the subtract sign, but nevertheless, they still got 0.39 grams of hydrogen. And now they calculated the empirical formula. So they found the number of moles of each of the different elements. Okay, and they got the same values. And then they found the smallest ratio. So the lowest number of moles was the sulfur. And then they divided everything by that. And they found the empirical formula to be C4H4S. And they noticed that this was the same formula as the molecular because they had identical molecular masses. Okay, so this solution is correct. Okay, so question number 5. What is the name of the ionic compound AlBr3? Okay, so when we have an ionic compound, when we name ionic compounds, we first want to name the cation, which is our metal. And then we want to name our anion, which is our nonmetal. And for the anion, it will have the suffix of "ide." Three, if we have like a transition metal that can have multiple oxidation states, then we can specify the metal charge in parentheses. But in the case of aluminum, it only has the charge of 3+. So we don't have to worry about the third step. But let's try to name the compound in the question. Al is the metal aluminum. So we name that first. And then we name the non-metal, which is bromine, but instead of, we're going to change the suffix to "ide." So the name of this compound is aluminum bromide. So the junior tutor said that for binary ionic compounds that contain two types of elements, the compound is named by writing the name of the cation first, followed by the name of the anion with the prefix "ide." For the example above, aluminum Al is the cation aluminum, Br is the anion bromine. Therefore, the name of the compound is aluminum bromide. Aluminum bromide is a highly water-soluble crystalline that is mostly used for water treatment processes. Yep, so the solution is correct. Okay, so question number 6. Aside from hydrogen atoms, what else is needed to form hydrogen bonds? So hydrogen, I think they mean like hydrogen bonding, maybe. So when you have hydrogen bonding, we also need a hydrogen atom that is attached to an electronegative atom. So some examples would be like nitrogen, oxygen, or fluorine. So the reason we need an electronegative atom is because we need to create dipole moments in our molecule in order to have hydrogen bonding take place. So I'll just have a common example showing the water molecule. So you'll see that 2 hydrogens are attached to oxygen. Obviously, we know water is H2O. But also, oxygen is much more electronegative than hydrogen is. So it will pull the electrons. It has an uneven share of electrons in the bonds with hydrogen. So the side that contains the oxygen has a partially negative charge, and then the side of water that has the hydrogens will have a partially positive charge. So we can show that this water molecule has an overall dipole moment in the direction towards the oxygen. So what happens with hydrogen bonding is that when we have a second water molecule, which I'll draw down here, it also has a partially negative side and a partially positive side. And hydrogen bonding is actually the attractive force that these partially charged atoms feel. So that partially positive charge on the hydrogen will be attracted to the partially negative charge of oxygen on a different water molecule. So then you can kind of show how all of these water molecules can be kept together because of this thing called hydrogen bonding. Yeah, so you can see that it is this intermolecular force, and that is why we need both hydrogen and also this electronegative atom, because if we had, let's say, a methane molecule, this is a nonpolar molecule, so that same dipole moment that happens in the water won't take place in a methane. Let me just put like an X in between. So let's see what the junior tutor said. Hydrogen bonding is a dipole-dipole interaction of molecules to a hydrogen atom. The bonding results from the attractive force of hydrogen, which is covalently bonded to a very electromagnetic atom, such as nitrogen, oxygen, or fluorine, and an electronegative atom. Oh, yep. And then for molecules containing hydrogen atom bonded to nitrogen, oxygen, or fluorine, the large difference in electronegativity between the atoms leads to a highly polar covalent bond. Therefore, aside from hydrogen atoms, polar covalent bonding is also essential in forming hydrogen bonds. Yep, so this solution is correct. Okay, so question number 7. A certain ionic compound is made entirely of aluminum and oxygen. What is the formula for this compound? So aluminum is a group 3 metal, and its ion therefore has a 3+ charge. In the case of oxygen, it tends to have a 2- charge. Since it has 6 valence electrons, it usually wants to accept 2 more electrons to have a -2 charge and a full valence shell. So if we have aluminum 3+ coming together with oxygen, which has a 2- charge, we want to somehow neutralize these charges. So to do that, we would need 2 aluminum 3+ ions reacting with 3 O2- ions. So that should cancel out the charges of the 2 ions. And then our final formula is aluminum 2O3. So I'm just also going to name it aluminum oxide. Okay, so let's see what the junior tutor said. An ionic compound is a compound that is formed when 2 ions are joined together. In this problem's case, the elements that entirely make up the compound are aluminum and oxygen. Aluminum, being in the group 3A on the periodic table, tends to have a charge of +3. On the other hand, oxygen, being in the group 5A, no, that 6. Group 6A and a nonmetal, tends to gain electrons and will have a charge of 2-. In order to complete the octet, aluminum ion is aluminum 3+ and oxygen ion is oxygen 2-. Joining these 2 ions and through the cross multiplication of the charges, the formula for the compound made by these 2 ions is Al2O3. Yep, so this solution is correct. Okay, so on to question 8. Question 8 just asks, what are the different functional groups in the molecule? So it doesn't look like they show a molecule, but I guess what the junior tutor said was they just showed almost all the different functional groups you can have ever in a molecule. So this is a very large, probably fictional molecule that they have here, showing all the different types of functional groups that you could have. So when we have an oxygen in between two carbon groups, this is known as a carboalkoxy group, or as an ether. An amide group is when we have carbon double bonded to an oxygen and has an amine group as well. OH is an alcohol group, so this is also known as hydroxyl group. When we have sulfur covalently bonded with oxygen, this is a thiol. When we have a double bonded oxygen on a carbon, this is a carbonyl group or a ketone. Carbon just bonded with NH2 is an amine group. When it's bonded with either chlorine, fluorine, or bromine, this is a halo group or like a halide. And they have amine group again. So functional groups are specific groupings of atoms within molecules that have their own characteristic properties, regardless of the other atoms present in a molecule. These functional groups will undergo the same type of reactions regardless of the compound of which they are part of. However, the presence of certain functional groups within close proximity can limit reactivity. Some of the most common functional groups and their properties are, so they show hydroxyl, that is polar, and it is made up of one hydrogen and one oxygen. Amide, so presence NH2, carbonyl. So this is also known as a ketone. Carboxyl. The carboxyl group is made up of a carbon double bonded to OH. They have the amine, thiol. I think they meant to make, this should be an oxygen. Like if you look at an actual carboxyl group, it has a double bonded oxygen on the carbon and an alcohol group. This is also known as a carboxylic acid. So the same thing down here when they say carboalkoxy, it's actually not a double bonded carbon. It is a carbon that is double bonded to an oxygen and single bonded to another oxygen in the middle of a chain. So this is carboxyl carboalkoxy. So I'll just take note. Maybe it was just a typo. For the halo Chlorine can be any halogen. And then finally, an aldehyde is double bonded oxygen and a single bonded hydrogen to a carbon. Okay, so this solution in depth and informative. However, for the carboxyl and carboalkoxy, this even how? Yeah, I guess it's just not that common of a word. Carboalkoxy group. Okay, so I just said that the solution is very in-depth and informative. However, for the carboxyl and carboalkoxy groups, they contain a carbon that is double bonded to an oxygen and single bonded to another oxygen. Carboxyl groups have the formula COOH, while carboalkoxy groups have the formula COOR. So I guess I'll still say this solution is correct, though. Okay, so those are all the questions for this session, and if you enjoyed today's Q&A and you'd like to be notified of when we do this next, please hit the subscribe button and notification bell below. If you'd like to submit a question of your own, then check out the links in the description. And also, if you enjoyed today's video, go ahead and give it a thumbs up and a comment, and you can share it with your friends and classmates if they needed any help with chemistry. This has been Donna from OneClass, and I hope to see you soon. Bye.